Hello, ladies and gentlemen. Welcome back. Folks, today you are in for a treat. We are going to be talking about a new dance move I'm trying to learn, the random walk. It also happens to be a time series model where every step you take is completely random. The path is driven by the sum of independent events, usually represented by white noise. To visualize this, let's play a simple dice game. Here are the rules. You pay $7 to roll 2 dice. Your payout is whatever the sum of those dice is. So we'll denote the sum of the dice rolls as C star sub t, and your net winning as C sub t. C sub t is just the dice sum minus the $7 fee every time you roll. Your total capital after time t is given by y sub t. We define your capital at time t as your capital at time t minus 1 plus the net winnings at time t. Now, let's say you start with $100. We'll denote this as y sub 0 equals 100. Let's play the game and see how it goes. Drum roll, please. First roll, you get a 10. Minus the $7 fee, you profit $3. Good job. Save up some more, and maybe you'll be able to afford a latte. Second roll is an 8. You make $1. Your balance goes to 104. Try not to spend it all in one place. Third roll is a 7. You break even. Your balance stays flat. Last roll is an 11. After the $7 fee, you profit $4. Your balance goes to 108. Cha-ching! Now we can get that latte. Let's continue to play the game and see how it goes with more rolls. Unfortunately, I can't roll dice by hand all day since I have to work on my dance moves. So let's just simulate it. This jagged line? That's your luck after a night of gambling. Not bad. It's the sum of all your past wins and losses. While each roll is independent white noise, the capital itself is highly correlated. It remembers where it's been. That's the random walk. If we run this simulation a few more times, you see they all start at 100, but then they just wander off. It's unpredictable. That's the beauty and the terror of the random walk. Since we paid $7 to play, and the average payout is also $7, we expect to break even in the long run. Of course, there's some luck involved, as you can see from the simulations. Just for fun, let's give the house some edge. Maybe an entrance fee of $8 instead of $7. We'll just extend our y-axis down here. Maybe some more. Okay, I think that's good. Bring on the pain, baby. And that's why we don't gamble. Wait, maybe just one more. As I was saying, and that's why we don't gamble. So how do we spot a random walk model? Based on the source reading, there are 3 ways to do it. First, use a control chart to detect patterns such as a linear trend over time or increasing variability. Second, if it is a random walk, differencing the series should give you white noise. Use a control chart on the differenced series to detect patterns. And third, compare the standard deviations. A random walk model will exhibit a higher standard deviation in the original series than in the differenced series, indicating a reduction in variability when differences are taken. In this section, we'll go through the difference between a linear trend in time model and a random walk model. Both can be used to model time series data. The main difference is in the error term. A linear trend in time model is defined as beta 0 plus beta 1t plus epsilon t, where epsilon t is a stationary white noise process. This is a simple model that can be used to model a time series with a linear trend. Our goal is to compare it against a random walk model. Recall that the random walk model is defined as y0 plus all the white noise terms up to time t. Since Ct is a white noise process, we can further decompose Ct into a drift and error term where mu c is a constant and epsilon t is a white noise process. A quick aside, the source material defines Ct as a white noise process, but it's using the term loosely to also include a white noise process with drift. This is a little bit confusing if you're reading the source material, but just know that CT is technically a white noise process with drift, even though the source material calls it a white noise process. Moving on, we define a new variable, ut, as the partial sum of the white noise process epsilon t. Since ut is the sum of white noise terms, it is itself a random walk process. With some algebra, we get the following equation. Note the similarities between the random walk model and the linear trend in time model. y0 is a constant, comparable to beta 0, and beta 1t is analogous to mu ct. However, the main difference is in the error term. When we plot the terms, the error term epsilon t in the linear model is white noise. It is bounded and stable. But u, it is the partial sum of white noise terms and follows a random walk. This accumulation is what makes it non-stationary. Okie dokie, let's now talk about forecasting for a random walk. So we are at time t, and we want to know what happens at time t plus L. This is the equation we can use to calculate the future value. The future value is just where we are now, plus a bunch of future random noise. The equation follows from the random walk model, where we essentially substitute t with t plus L. But since we don't actually know the future noise, we have to estimate it. Recall from the video lesson on white noise that the point estimate forecast of a white noise process is the sample mean of the random noise terms from time 1 to time capital T, which we denote as C bar. Since we're adding L periods of noise, we multiply the sample mean by L to get the point estimate forecast at time T plus L. We then add this to the current value to get the point estimate forecast. Let's visualize this. Unlike white noise, a random walk has memory. Here we observe a random walk over 20 periods. Notice the upward trend? To forecast, we take our current position and project the average drift forward. Because we multiply C bar by L, our point forecast forms a straight line. Of course, a point estimate is not always accurate. Sometimes we want a prediction interval to give us a range of values within which the true value is likely to lie. This formula gives us our approximate 95% prediction interval. The first part is the point estimate forecast. The second part is the uncertainty term, where 2 is the approximate critical value for a 95% confidence level, and SC is the standard deviation of the white noise terms from time 1 to capital T. Notice the square root of L adjustment factor. It's there to adjust for the fact that the further in time you try to predict, the less you know, so the prediction interval gets wider. Let's look at the prediction interval on the graph. Unlike white noise, where the interval stays the same width, here the uncertainty grows with time. At 1 step ahead, the range is small, but at 5 steps ahead, the range expands significantly due to that square root of L factor. Let's look at an example. We have a random walk process observed up to time 50. The current value is 85, the sample mean of the white noise is negative 0.30, and the sample standard deviation is 3. We are asked for the approximate 95% prediction interval for the value at time 60. First, we calculate the point forecast. We take the current value and add the expected drift over the forecast horizon. Our horizon L is 10 steps. Substituting our values, we start at 85 and add 10 increments of negative 0.3. This gives us a point estimate of 82. Next, we construct the 95% prediction interval. We take our point estimate, plus or minus 2 standard errors. We use our point estimate of 82. Remember, the standard error grows with the square root of time. Calculating the margin of error, we get approximately 18.97. Applying this margin to our point estimate of 82, we get our final interval, roughly 63 to 101. Let's visualize this solution. Here is our random walk ending at 85 at time 50. The point forecast drifts downward because C bar is negative. The 95% interval expands as a cone. At time 60, this cone spans from 63 to 101. Let's look at another example from the Society of Actuaries sample questions. This one is quite tedious, so let's walk through it step by step. Here's the problem statement. We are given a random walk model, y sub t, and observed values from time 1 to 10. We know the series starts at 0. We need to calculate the standard error for the forecast at time 19. First, recall that in a random walk, the noise term c sub t is simply the difference between consecutive steps. By subtracting each value from the previous one, starting with y0 equals 0, we recover the entire white noise series. Here, we get the values for C1 through C10. Next, we calculate the sample statistics. The sum of the noise terms is 30, so the mean is 3. For the sample standard deviation, we sum the squared differences from the mean and divide by n minus 1. We need the forecast at time 19, which is 9 steps ahead. The standard error is the standard deviation times the square root of steps. Substituting our values, we multiply 4/3 by the square root of 9. The result is exactly 4. Let's see what this looks like on a graph. Here is the observed path of the random walk from time 0 to 10. The point forecast continues with the average drift of 3 per step, reaching 57. At step 19, the standard error is exactly 4 units. Note that this is not the prediction interval width, since we haven't adjusted for the confidence level. The question simply asked for the standard error, not the prediction interval. Random walks are likely to show up on the exam, so be sure to get lots of practice. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.